Okay, this is for Physics 5B, Sacramento State, summer 2020. It's July 26, 2020. So I forgot to put up assignment place for you to turn in assignment 4. So it's here. Okay, and then assignment 5 is the one we're working on now with this video. And you can find it here, online worksheet number 5. You can turn it in right there. And then when this is all done, I'll update. This will be updated. So if you're watching this video and you haven't downloaded the newest PowerPoint, where it's going to be the new one that's going to complete chapter 20. Okay, so on the PowerPoint, so we ended up on Ohm's law. Now we're up to resistance and resistivity. So the resistance is dependent on the geometry and the material of the object the current is passing through. Geometry-wise, it depends on the area and the length. And common sense tells us that the greater the area, the smaller the resistance will be, because that gives the electrons more room to pass through. Also, common sense says the longer the length it has to pass through, the greater the resistance is going to be. Okay, so the resistance is proportional to the length. The greater the length, the greater the resistance, but inversely proportional to the area. Greater the area, the smaller the resistance, because the electrons will have more area, more room to pass through. Okay. So here are some resistivities. So they got a table in the book to look them all up. This is right out of your textbook. Resistance also depends on the material of the object. Resistance also depends on the material of the object, such as a wire, is made out of. So that's the resistivity, that's rho, okay? R equals rho times length over area, where rho is the resistivity of the material. So they've gone into labs, they've used all these materials, and they've measured their resistivities, and that's how you have a table like this in your textbook. 1 meter of copper wire, 1 meter of copper wire has an area of about 3.14 times 10 to the minus 4 meters squared. What is its resistivity? Well, okay, so the length is 1 meter. There's your 1 meter right there. The area is going to be 3.14 times 10 to the minus 4 meters squared. So there's that guy right there. Well, corresponding to that guy. Then your resistivity for copper, you've got it right there. 1.72 times 10 to the minus 8. So you got it right here. Okay, so then, and then we don't have an answer. I don't know why I didn't put an answer down there. That's all you do. You just go that number times that number divided by that number, and you'd have the resistance of that wire. The resistivities in the above table were for materials at 20 degrees Celsius. Okay, so the resistance is going to change with changing temperature. The temperature increases as the resistivity also increases. This is because at higher temperatures, the atoms and molecules that make up the material, like a metal, vibrate faster and over a greater distance. So there's increasing likelihood of interactions between the charges and the nuclei. So the electrons are moving through, and the more energy that is given to the nuclei through higher temperature, higher thermal energy, the more they're vibrating, and the more there's going to be interactions between the electrons and the nuclei. That's going to cause greater resistance to the electrons trying to get from one place to another. It's going to zap more energy out of the current. Okay, so what we do is the rho would be equal to, this is the rho at 20 degrees Celsius, okay? This is rho at 20 degrees Celsius. 1 plus, then this is alpha. This is the constant for the how much the resistance goes up, times the delta T, how much the current went up. Where rho 0 is the resistivity at 20 degrees Celsius. So what would be the resistivity of a copper wire if the temperature went from 20 degrees to 30 degrees, okay? So you've got rho, then 1 plus alpha delta T. So the rho for copper wire is 1.72 times 10 to the minus 8. We saw that earlier. Then 1 plus, and if you look it up in the book, 3.9 times 10 to the minus 3 over degrees Celsius. And then from 20 degrees to 30 degrees, delta temperature would be 10 degrees, okay? So you get a resistivity of 1.79 times 10 to the minus 8. So it went up a little bit. It went up from 1.72 times 10 to the minus 8 to 1.79 times 10 to the minus 8 when you increase the temperature from 20 degrees to 30 degrees. So since resistance equals rho L over A, and L and A do not change much with temperature change, okay? I mean, yeah, you've got thermal expansion, we've had that, but it's not going to be significant. In other words, it's going to be numbers that are out past the decimal place that are not what we're dealing with. We're only dealing with 3 digits of accuracy here. So you can replace it with just R equals R0. So you're just replacing the rho. So you solve for rho here. Rho would be equal RA over L. But then the RA over, then the A over L would cancel out, and you're left with R equals rho 0, 1 plus alpha delta T. Okay, is that it? Okay, so I think we can do a couple of problems here. So this is this one. Okay, the diameter of a 0 gauge copper wire, don't worry about the 0 gauge, you can look it up and see what that means exactly, but the diameter is 8.252 millimeters. Find the resistance of a 1 kilometer length of such a wire used for power transmissions. Well, the first thing is they gave it to us in we could do the diameter, but most people use pi r squared to find the area of a cylinder, of a circle. So we just take that 8.252 and divide it by 2, okay? So here's what they did here. So now we've got the radius instead of the diameter. So down here you got the resistivity. There's the equation we use. Resistivity of copper wire, you see it up there, it's 1.72 times 10 to the minus 8 ohm meters times, and then that's a kilometer, 1 times 10 to the third meters, pi times, and then we square this, pi r squared, square this guy. So the resistance is going to be 0.322 ohms. Okay, so that's how you find the resistance. You know the resistivity, you know the length, and you know the area. You just plug into that equation and you got the resistance. Okay, what current flows through a 2.54 centimeter diameter rod of pure silicon that is 20 centimeters long when 1.00 times 10 to the third volts is applied to it? Okay, so we find the resistance first. The resistivity of the silicon now we got silicon, is going to be 2,300 ohm meters. Okay, silicon is not a conductor. See, copper has a very low resistivity. It's a conductor. We want this to be low if we want it to conduct. Silicon is an insulator, so that's going to be big. Okay, so you take that number times, you want to go through 20 centimeters would be 2 meters, 0.2 meters, 2 times 10 to the minus 1 meters. And then that's supposed to be pi right there. See, pi, I hit the wrong thing. So then 1.27 times 10 to the minus 2 meters squared. So that was the radius, because you got to divide the 2.54 in half. So you get this. And then you get 9.078 times 10 to the 5th ohms. So silicon has a big resistance because of its resistivity. It's an insulator, not a conductor. Then I equals V over R equals our 1,000 volts divided by our resistance we found right here. So you'd have 1.10 times 10 to the minus third amps, or 1.10 milliamps running through there. Okay, a resistor made of nichrome wire is used in an application where its resistance cannot change more than 1% from its value at 20 degrees Celsius. Over what temperature range can it be used? Alright, so we start off with this equation here. Now, this number, this is going to be R equals R0 plus or minus. You can think of it as plus or minus in this case, alpha delta T. So we can't let it go up. We'll say we can't let it go up or down 1%. So we'll see how much can we not let it go up. Alright, so as a result, we go R equals R0, so it can't change by more than 1%. Okay, so going up by 1% or down by 1%. So our alpha delta T has to be 1.01 R0 at the maximum. Okay, so alpha delta T equals 0.01. That'd be 1% of 1. Okay, that's as most as it could change. So we solve for our delta T. How much can the temperature change? 0.0100 divided by alpha. We look it up in a table that's in the book. That'd be 1.00 divided by 0.4 times 10 to the minus 3 delta degrees Celsius. We get 25 degrees Celsius. So that means it can't go up. If it's at 20 degrees Celsius, we're at 20 degrees Celsius, it can't go up more than 25 degrees Celsius, so it can't go up past 45 degrees, and it can't go down more than 25 degrees Celsius, so it can't go below minus 5 degrees Celsius, okay? That would be the range, plus or minus 25 degrees Celsius. And the table, hold on. Okay, here's the table that's in the book. It's in this section 20.3. This is the alpha, so there you have them all listed right there in your book. Okay. And which one did we just look at? We just looked at nichrome. So nichrome is there. 0.4 times 10 to the minus 3, and that's what we use. 0.4 times 10 to the minus 3. Okay, let me take a break for a second. Okay, so now we're going on to section 20.4, electric power and energy. We call it power is the rate at which one form of energy is converted into another form of energy, the rate at which work is done. Okay, so basically it's the same thing you had in your first semester of physics when you talked about going back and forth between potential energy and kinetic energy. It's just in this case we're going from one type of energy into electrical energy, or from electrical energy into another type of energy. So it's the same thing. It's still power in watts, nothing new here. This is the same exact concept you learned about in 5A, only now it is applied to electrical circuits. When you buy a 60-watt light bulb, you expect that the light bulb will convert 60 joules of electrical energy into 60 joules of light energy every second that goes by. Okay, so you're just converting electrical energy into light energy, and so it's the same thing. Why isn't this going down? Okay, we go. Okay, so here are the equations we have. They're on your handout, or the document that you downloaded, this one here. It should be on here someplace. I think they're here. Okay, so there's what power is. So power, that's, you can think of it as potential energy over time, or QV. Remember, potential energy is the charge times the voltage over time. And you've got Q over T times V. Well, what's Q over T? That's current. Q over T is the current. So power equals current times voltage. Okay? So making use of Ohm's law, voltage equals I times R, I equals V over R. So you just plug, for example, if you plug IR in for V, you get I squared R. If you plug in V over R for I, you get V squared over R. Okay, so 3 different ways to get the power. So if you know 2 of the 3, the current, voltage, and resistance, if you know 2 of the 3, you can easily figure out the power. Obviously, if you know 2 of the 3, you can get the third one and figure out power with any equation you want of those choices. Okay, electrical power. So now you have the cost of energy. Your book has a big section about it. So when your electric bill comes, you will notice that the power company probably used units of kilowatt hours. This is a unit of energy. It's not a unit of power. People hear the word kilowatt in there, they forget the word hour is in there. Remember that power is energy times energy divided by time. So energy is power times time. So this is units of power times units of hours. Okay? So obviously kilowatt hour, when the electrical company SMUD or PG&E tells you use this many kilowatt hours, they're telling you how much energy you used. Okay, so 1 hour, that'd be 1 kilowatt hours, that's 3,600 seconds. So power would equal, say, 1,000 watts times 3,600 seconds. That'd be 1 kilowatt times 1 hour. Okay, so there's 1 kilowatt, there's 1 hour in seconds. So we convert that over to joules, and that would be 1 kilowatt hour is actually 3.60 times 10 to the 6th joules. Okay? Suppose your local power company charges 15 cents per kilowatt hour. Your TV uses power at a rate of 100 watts, and during the month you watch the TV for 6 hours per day. How much are you charged? Well, okay, so 30 days in a month, 6 hours per day, 180 hours. Then the energy would be power times time. That'd be 0.1 kilowatts times 180 hours. So you would use 18 kilowatt hours. Okay, so the cost for using the TV, what was it again? So many hours a day, 6 hours a day for a month. You'd pay $2.70 for that. Okay, so now we could probably go back and do some problems. Okay, what power is supplied to the starter motor of a large truck that draws 250 amps of current from a 24-volt battery? P equals I times V. 250 amps times 24 volts equals 6 kilowatts. Okay. How many watts is a flashlight that has 6 times 10 to the second or 600 coulombs pass through it in half an hour, 0.5 hours? Well, there's a 3,600 seconds in an hour, so in half an hour there'd be 1,800 seconds. So you take the charge divided by the time, and you would get 0.3333 amps. We also had a homework problem that did something like that, I believe. So power equals I times V equals the 0.33 amps times the 3 volts, or 1 watt. So how many watts does a flashlight have that passes 6 times 10 to the 2 coulombs pass through in 0.5 hours of use? So it's using 1 watt, 1 joule per second is what it's using. Okay, and then with a 1,200 watt toaster, how much electrical energy is needed to make a slice of toast? Cooking time 1 minute at 9 cents per kilowatt hour. How much does this cost? All right, so the energy is going to be power, 1,200 watts, times the time. Okay, 1 minute or 60 seconds. Okay, we've got the conversion right there. So 1 watt times 60 seconds, basically, you're going to use 7.2 times 10 to the 4th joules. So 7.2 times 10 to the 4th joules. We figured out what, up here, we figured out what 1 kilowatt hour was. We did it someplace. What did we do? Well, we figured out that it was 3.6 times 10 to the 6th joules in 1 kilowatt hour. So we start off with our joules. We do this, we have kilowatt hours. We're 9 cents per kilowatt hour. So it costs you 18 cents with that toaster to make a slice of toast. Okay, now that we need to move on for the rest of these. Okay, so now we are up to alternating current versus direct current. So far we have only dealt with direct current. DC current is what you would get from a battery, for example. The voltage and the current do not vary over time. They may decrease as the battery gets weaker, but they're supposed to stay constant. You get a 9-volt battery, you expect to get a pretty constant 9 volts out of it. It's not going to fluctuate. But with AC, alternating current, the voltage and the current do vary over time. When the energy is generated using turbines, it is AC current that you're getting. You get AC current from the outlets in walls. And your lights actually flash on and off. Most lights flash on and off really quickly. You can't tell they go off and on, off and on, off and on, but they do. So this would be DC. The voltage stays constant, the current stays constant. But for AC, they're fluctuating. You got 0 volts up to a maximum, down to 0, down to negative, up to 0, back up. The same thing happens with the current. Okay. So these are just off of the chapter 20. So there are these guys right here. They all are. Okay. So this is the voltage at any instant of time. It's going to be equal to the peak voltage, the maximum voltage, times sine of omega t. But omega is 2 pi times the frequency. So you put in 2 pi times the frequency. So at any time, if you know the frequency and you want to find what the voltage would be at any time, you go the maximum voltage. If it's like 10 volts maximum, then you would go sine of 2 pi ft to get the voltage. Same with the current. I just use Ohm's law. You plug in this and you get I equals I0 sine of 2 pi ft. That I0 again is the maximum. That would be on these guys over here. There's the maximum voltage right here. There's the maximum current right there. Okay, that'd be V0. They got them listed right there. V0, I0. Okay, and then we got them. Same thing. I put them down here too. Okay, so there they all are. So this omega here, 2 pi frequency. So we get the same equation you just saw. Root mean square. Okay, those are values for the voltage and current you would have. Oh, let me turn the TV down. I forgot I had it on. Okay, sorry about that. So now root mean square. So over time, you got these two circuits here. One's DC, one's AC. Now there are times when there's no power output by the AC circuit. Then you have the maximum power output, then no power output, then the maximum power output. So over a long period of time, you're going to have an average power output. Okay. Sometimes it's the maximum, sometimes it's zero, but it's going to fall in some place like this. It's going to be like some kind of average power output over time. So what the RMS, the root mean square, is, that would be the equivalent DC voltage and current that would give you that same power output over that same amount of time. Okay. So in other words, let's say that between these two, let's say we have 1 volt and 1 amp, we get 1 watt out to here. Okay. Here, okay, well, we're going to have way more than 1 watt, but then we're going to have 0 watts. So we're going to have way more than 1 watt, then 0 watts. So over a long period of time, though, let's say it averages out to 1 watt. You're getting 1 joule per second on average. Okay, what would be the equivalent DC voltage and current that would also give you that? That's the root mean square number. Okay. So root mean square, basically it's going to be, there we go, it's either the I0, the maximum current in an AC circuit, divided by the square root of 2, which is the same as 0.707 I0. So you take the maximum current you get in a circuit, AC circuit, either divide by the square root of 2 or multiply by 0.707. That would give you the root mean square current, the current you would have in an equivalent DC circuit that gives you the same power output over time. And the same thing's true for voltage. To get the VRMS, just go V0 divided by the square root of 2, or 0.707 times the maximum voltage you get in an AC circuit. Okay, VRMS equals IRMS times R. R doesn't change. It's going to be the same whether it's an AC or DC circuit for the most part, and so on. I don't know why I have RMS. Okay, so I got that there. I don't know. Now, P average, okay, we could think of it as either I squared R or I RMS times V RMS, or V RMS squared, AC power to the resistor for an AC circuit. Okay, and then I got the V0, I got this again. So V0, okay, if you want to go the other way, we can do this with I0. I don't have I0 on here, but we just solve for V0. So if you know what the VRMS is, you would just multiply it by the square root of 2, and that would give you the maximum voltage in an AC circuit. And that's it. Alright, so coming back over to here. Okay, a certain circuit breaker trips when the RMS current is 15 amps. What is the corresponding peak current? So in other words, over a long period of time, you get your average power output from the circuit, and the equivalent current would be 15 amps. So then if it's going peak to peak, it goes all the way up to 21.2 amps. So it's 21.2 amps down to some point 15 amps, at some point down to 10 amps, some point down to 0 amps. Then it goes negative 10 amps, negative 15 amps, negative 21.2 amps. But over a long period of time, it averages out to be about 15.0 amps. Okay. Now this one here, a North American tourist takes his 25 watt, 120 volt AC razor to Europe, finds a special adapter and plugs it into a 240 volt AC. So in other words, it's designed for North America. I guess that means Mexico, United States, and Canada. I don't know if Mexico's the same as the United States with that, or Canada. I don't. Anyway, we know in the United States we're 120 volts. Okay, you take it to Europe where they're at 240 volts. All right. So assuming constant resistance, what the power does the razor consume as it is ruined? The guy's going to ruin his razor. So in the United States, this is what the resistance would be. Okay, we've got the power it's rated at. It's supposed to be this power here, 25 watts, and it's supposed to be 120 volts. So we have power equals voltage squared over R. We have voltage, we have power, we're looking for R. So we solve for R. So V squared over power, 120 volts divided by 25 watts. It's going to be inside that razor 576 ohms. You take it to Europe, plug it in with your adapter, Your 25 is meant to be a 25 water. Okay, well now let's use that same resistance because the resistance doesn't change, but now you're plugging it into 240 volts instead of 120 volts. You double the voltage. So you double that, you got 240 squared. So you've got 100 watts. Your 25 watt razor, now you're trying to run it with 100 watts. 100, instead of giving it 25 joules per second, you're giving it 100 joules per second. That's why it gets ruined. Okay, and that's it. Okay, so the plan now is to have a quiz on, let's see. Oh, yeah, okay, here's my plan for now. Okay, we'll have a quiz on Thursday. We won't have a quiz on Tuesday. We'll have a quiz on Thursday. Then we'll have our second exam the following Tuesday. Okay, I'm giving all my finals at Sac City on Thursday. I think no Monday and Thursday. The Wednesday and Thursday. So I'll be done with Sac City finally. All right, so I'll be done with them, and then instead of giving you guys an exam at the same time, I'm giving them an exam. So I got to make up the exams. I'm going to have us just do a quiz. It doesn't take me as long to make up the quizzes, and then our exam will be Wednesday. Okay, so I'm going to start. Let's see, it's about 4:40. Okay, let me shut down now. So I'll say goodbye for now, and I'll talk to you later.